Chapter 17, Part 1, Solubility. So a lot of processes depend on a precipitation reaction or a soluble salt only dissolving slightly. So we call these slightly soluble substances. They dissolve only a partial amount in water typically. So because they are slightly soluble, they form an equilibrium reaction with water. Some of it stays whole, and then a small proportion of it does break apart or dissolve into the ions. So when we have this reaction here, solid calcium oxalate, it's a slightly soluble, so some of it will break apart into the ions calcium and oxalate, but a majority of it stays whole as the CaC2O4. So because this is an equilibrium reaction, we can write an expression for that. So the K expression we write is called the KSP, which stands for the solubility product constant. So it is equivalent to the concentration of the ions and that's it. We don't include the solid because it is a heterogeneous. We don't include the solid, we only include the aqueous substances. So in general, it is going to be the product of the concentrations raised to a power, and that power is going to be determined from its stoichiometry. How many ions of each is formed when that substance does dissolve in water. So if you have PbI2, in water, it's going to split apart into leads. Lead has a charge of +2 in this case, and iodine ions, and because it was I2, we have 2 of these iodines that are going to form. So our K expression is the concentration of each raised to how many we had. So Pb is raised to the first power, but our I is going to be squared because this is a coefficient of 2. So two important distinguishers are between solubility and the solubility product constant. So solubility, whose symbol is a capital S, it is an amount. It's how much will dissolve to form a saturated solution. So how much can we dissolve before no more will dissolve? We can express it in terms of grams of solute per liter, or something called the molar solubility, which is moles of it per liter, which of course is equivalent to the concentration or molarity, because they are both moles per liter. The solubility product constant, or KSP, is an equilibrium constant for the equilibrium reaction that forms between the solid and the ionic things that it dissolves into. So we have a 1 liter sample of a saturated calcium oxalate, so as much of it has dissolved as is going to dissolve. So this solution contains 0.0061 grams of the salt. We want to calculate the KSP. So what we want to do first is figure out what the molarity or the solubility of this in terms of molar solubility. Right now we have how many grams per liter, but we need this to be moles per liter because the numbers we plug into ice boxes are concentration or moles per liter. So we just care about changing the moles or the gram part into the moles. We don't care about the liter. We want to keep that there. Okay, so that's the initial concentration. And then initially, like that. Now what we are going to assume is because this is a saturated solution, all of my calcium oxalate is going to dissolve. So that means that every time that the CaC2O4 is in water, it's going to break apart. So the concentration at the equilibrium is going to be the same as what we started with. So this is going to go up by some amount, this is going to go up by some amount, but we know what it's going to end up being for both. Okay? Because all of this is going to break apart if it's saturated. None of it is going to remain. whole. So our K expression for this reaction would be our two ion concentrations at equilibrium, which we know what they are. They're both the same. So we can say this is squared. So we know what this we know what this value for KSP is. Okay, let's say we have a lead iodide dissolve. So it is found that we know how many moles are going to dissolve in 1 liter, so we know the concentration. What's the KSP? So let's write our reaction. Okay, so our molarity is going to be our molar solubility. They are the same thing in this context, moles per liter. Since we know exactly how much is going to dissolve, right, that's going to go up by 2x because there's 2 of them. We know that this is going to be the same. And this one has to be this twice as much. Because for every 1 PbI2 that we have, 2 ions form. So we want to multiply its concentration by 2. So now our K expression where we got to square it to account for the fact that we get a coefficient of 2. So our PB was 1.2 times 10 to the negative third. This is going to be 2.4 times 10 to the negative third when we double it. So we can plug that in. And then we got to square that also. So there is all kinds of tables you can find for most substances to figure out what the KSP for various ionic compounds are. We can also work backwards, which we'll see in a second, that if you know the KSP, you can figure out how much will dissolve for a given amount of water or what the solubility can be. You can also compare salts based on their KSP values. Smaller KSP means it's less soluble in water, or less will dissolve in a certain amount of water. So let's work backwards. So calcium fluoride, we know the KSP. We want to figure out the solubility, which is the grams per liter. So we know what the KSP is. Okay, so we're going to start with our KSP expression. So in this case, it's going to be that. So what we're looking for is the molar solubility of CaF2, which is the same as the concentration. So really, this is our unknown, what we're starting with. We want to know how much of that we had. Okay, initially we had 0. We know that this is going up by that same amount of x, and this is going up by the same amount of 2x since we have a coefficient of 2. So let's plug those values into our K expression. So our KSP, so our Ca is x, and this is going to be 2x squared. 2x squared in parentheses is the same as 4x squared, right, because you got to square both the 2 and the x. We can combine the x's to do 4x cubed. So now we can solve this. 3.4 times 10 to the negative 11th is equal to 4x cubed, and solve for what x is equal to. So you want to divide by 4 and then take the cube root of whatever that number is. So you get the value of that for x. So x is equal to the molar solubility. So that's how many moles per liter we can dissolve. But the question wanted you to find grams per liter. So we have to do a quick little conversion. I'm going to go over here and do it. to figure out what that'd be in terms of grams per liter. So if we add up calcium fluoride's molar mass to give our conversion, it's 78.1. So we can dissolve 0.016 grams of that per liter of water. Okay. Oh. Okay. Estimate the solubility of lanthanum iodate and calculate the concentration of the iodate in equilibrium. Okay, so three iodates for every lanthanide. Okay, again, we're trying to figure out what we started with. These are going to go up by x and 3x. Okay, so our KSP expression is 6.2 times 10 to the negative 12. This is x. This is going to be 3x cubed, which is going to be 3 cubed, which is what, 27x cubed, which would be 27x to the fourth if we combine our x's. So divide by 27, and then take the fourth root of that. So that's how many moles per liter we can dissolve. Okay, the solubility didn't tell you to specify, so we can keep that. We also want to calculate how much iodate is in equilibrium, which in this case is equal to 3x. So that is how much of my iodate there is going to be at equilibrium.